So yeah. Okay, so what were we talking about 2 weeks ago? Peshtigo. Yeah, I think we should finish that up. All right, the Holocene Working Group. Who remembers what that is? Bill, you know? What was the Holocene Working Group? We talked about them a few months ago. Who were they and what are they doing? Okay.
They were in Germany, if I remember.
Well, they're an international group. There's about 25 of them. And they're from all over the world. Holocene Working Group.
Well, this is about the Burkle Crater, wasn't it?
Bill, thank you. Thank you. They're the guys who are working on the Burkle Crater. Okay, the Burkle Crater's got to be one of the most important scientific discoveries of the 21st century so far.
But they're not just focusing on that, are they?
Oh, no. In fact, I have a recent publication by 5 of them. From Los Alamos, from Lamont Doherty, from the Tsunami Laboratory of the Russian Academy of Sciences, and from Australia, the University of Wollongong, if that's how you say it. And what the Holocene Working Group is doing, Holocene, before we go further, let's define the Holocene. Okay, the Holocene is the last 10,000 years of the geological time scale. It's the one we're in now. It means the Holocene means the whole of recent time. And what was the Holocene preceded by?
Pleistocene.
The Pleistocene, right, which was the second most recent. The Holocene, we just said, was 10,000 years, is 10,000. We're still in it, right? The Pleistocene that preceded it, the epoch that preceded it, how long was that? How much?
A lot.
A couple of million years. A couple of million years. What distinguishes Holocene from Pleistocene?
Temperature, world temperature.
Well, as it'll turn out, I think that once we look at this from the broad perspective, we're going to see that the Holocene is nothing more than a sub-part of the Pleistocene. The separation of Holocene and Pleistocene goes back to older models, gradualistic models, where it was assumed that there was a long period of glacial ages, slowly shifting into glacial ages, slowly shifting out, and the last one ended between 10 and 20,000 years ago, and then inaugurated a whole new geological period, which was given the name Holocene. Well, as we look back over the last 2 million years, which is what characterizes the Pleistocene, if you go to the Pliocene, which preceded the Pleistocene, it was a time of balmy warmth all over the planet, with some interruptions, of course. But we can go back, in fact, back in the Pliocene is when you had hippopotami basking in the Thames River up in England. So it was obviously a very, very different climate. Okay, something happened around 2 million years ago. And whatever it was that happened, it changed the whole character of the global climate, because it triggered this seesawing succession of swings back and forth into deep glacial ages and then abrupt swings out of them into periods of interglacial warmth, such as we are in now. As knowledge has evolved and as we've gotten a more detailed and precise look at the chronology, what has changed is this. First of all, the number of glacial interglacial cycles within the last 2 million years has gone from 4 to at least 40. To at least 40. Now that's a pretty significant change. And that shift has occurred probably since most of us were in school. You know, since the 40s, 50s, 60s, even into the 70s. Okay, so that's been a major shift. The other thing is how quickly it changes from glacial to interglacial and back again. Again, in the old gradualistic models, this was a process that took typically, if you read the old literature from the 40s and the 50s and the 60s, they're talking about time spans that would be measured in tens of thousands of years. With radiocarbon dating, that all began to change. Radiocarbon dating came along in the 1950s. With radiocarbon dating, it became possible to start looking at these transitions and their precise chronologies in much greater detail. What happened is what was based before on slowly evolving astronomical cycles. How many of you have heard of the Milankovitch cycles? I mean, maybe we've talked about them in here. What are the Milankovitch cycles, Doris? Milankovitch was a mathematician, Eastern European mathematician, early part of the 20th century, who did calculations based upon changing orbital geometry. Orbital geometry changes because we all know that the Earth has a tilt. Right now it's at about 23.5 degrees. That tilt is surmised to change between roughly 22 and 24.5 degrees over a period of about 40,000 years. There's also the ellipse around the sun. Earth's orbit around the sun is not elliptical. Right now, the Earth is actually the closest to the sun on January 2nd and farthest away from the sun 6 months later. Now that elliptical relationship between Earth and sun changes over a long cycle of time. Then the third cycle was the changing position of the precession of the equinoxes, the precessional cycle. What Milankovitch did was he took those three cycles and he worked out complicated mathematics and determined that there was this slowly changing flux of heat to the surface of the Earth as the result of these changing geometries. So what they did is they set up a whole elaborate chronology of climate change that was, the term they used was tuned to the Milankovitch calculations. So what they did was they assumed, and this is, we're talking pre-radiocarbon dating now, what they did was they assumed that when all the factors converged together to make the climate somewhat cooler, that was a glacial age. When all of these forces, the changing geometries, converged on the other end to make the climate warmer, then we were in an interglacial age. As it turns out, though, most of the time, the various forces cancel each other out to a great extent. Anyways, what they did was they then assumed that this long changing cycle, within it they had a 100,000-year cycle, then within that there was a 40,000-year cycle, and this is what, for half a century, the model of glacial interglacial changes was based on this Milankovitch calculations. So here comes the 1950s, the invention, Willard Libby invents the radiocarbon dating method, and they start dating stuff, okay? Suddenly the dates coming from the radiocarbon testing doesn't jive at all with the model they've got based upon the Milankovitch orbital geometry changes. Well, it created a period of confusion that lasted for about 20 years in which what you can see is this reluctance to let go of the Milankovitch model in spite of the fact that the data is accumulating that totally contradicts it. Well, finally it gets to the point where there's so much data accumulated that by now very few people, I don't think anybody anymore is saying that the Milankovitch cycle does anything more than it probably does have an effect, but not the kind of effect we've seen, for example, with the onset of the Younger Dryas or the termination of the Younger Dryas, where we're seeing changes in global average temperature of 8 to 10 degrees centigrade occurring within 3 to 5 years, possibly less. See, nowhere back in these Milankovitch models of things was there anything at all remotely like that. So what has happened is, unbeknownst to the public at large, is that scientists have been sitting in the background making these detailed models. The public education and even the academic institutions promote a certain worldview. And even though most people aren't geologists, every time you open a magazine article about a geological thing like the Grand Canyon, or you turn on and you watch a documentary, until the last few years, always the emphasis was on how gradually everything happened. You know, Grand Canyon was created gradually, over many millions of years. Well, how long would it take to cut that gash in the earth if you've seen Grand Canyon and stood down and looked down into Grand Canyon, from the south rim there, and you're looking down, or from the north rim, which is actually higher, you're looking down, over 6,000 feet? Well, okay, could that have been cut in the time span they allow for it, if it's only being cut at the rate that the present Colorado River is cutting it? I think not, personally. What you got to also realize is that the Grand Canyon sits at the edge of a plateau. 10 million years ago, the top of that plateau was below sea level. A Grand Canyon isn't going to be cut until that plateau raises up, and then it can start down cutting.
I've been down in the Grand Canyon and the balanced rocks in there, they had to be moved there under a massive flood situation.
And there have been, and now they're beginning to accept that there have been massive floods down the Grand Canyon. Yeah, I mean, within the last 10 years, there has been several geologists doing research and have concluded that there were massive floods. Now, of course, when you look at Grand Canyon, you're looking at a rock succession that is 1 billion years old. Now, clearly, Grand Canyon totally refutes the idea of a young planet that a lot of fundamentalist type people try to proclaim, and even invoke the Grand Canyon as evidence of it. However, to acknowledge that it might have taken hundreds of millions of years to accumulate the full sedimentary sequence that's exposed in the Grand Canyon, and never mind the hiatuses in them, which themselves may represent catastrophic events, that's not the same as how long it took to cut the gash into those rocks. We have the maximum of 5 million years to do it in. Basically, that's about the time period that the plateau has been uplifted. Now, the thing you've got to realize, and I hope everybody in the next near future goes and sees Grand Canyon at least once in your life. When you're standing on the rim of Grand Canyon looking down into it, you got to realize that there was another full mile of sedimentary rocks over your head originally. You're standing on a layer that's Paleozoic rocks, 250 million years old. Well, there were Cenozoic rocks that reach from 250 million up to 65 million, and the Cenozoic rocks on top of that. So you had a whole sequence of rocks that were from 250 million years old up to about 10 million years ago. And those rocks are completely gone. Now, if you go to who's been to Zion Canyon? Okay, in Zion Canyon, when you're looking at those sandstones there, that is the Mesozoic rocks that once continued southwards and overlay the rocks that are above. They were above the rocks that you would be standing on if you were standing on the rim of Grand Canyon.
Now, how do you know all this? Where are these rocks? I mean, how can you make a judgment on something that's not there anymore, that's a mile plus high?
We're going to send you with Dolores to Geology 101, or we're going to dig up the tapes from about a year ago and have you review those.
Take a stratigraphy class.
A stratigraphy class. They're layered. Well, okay, I'll elaborate, the 30-second elaboration. Essentially, you've got layers of rock, right? Now, I have a geology, I don't have it on here, I don't think, but let's say you've got layers of rock. Okay, on the south edge of the plateau, you've ripped away the Cenozoic layers, you've ripped away the Mesozoic, and exposed the Paleozoic.
How do you know you ripped them away? That's what we're asking.
They're gone. They're not there.
They're like that.
But somewhere else.
Because you can see, you can go north of Grand Canyon and you can see the staircase that was created.
Okay.
You can actually see that staircase.
Okay.
There's a place called Escalante National Monument. Go there. You'll see the staircase. Right? It'd be like if I piled up layers of carpet in here and then I cut one layer back and then I cut another layer back. So you have this staircase effect. And there are remnants too, but they were stripped away. They were stripped away before Grand Canyon could be cut. That's my point. In other words, you have to remove a mile of rock, and only then can you start creating the canyon. Now, we're talking about some serious erosion here, far beyond what you're going to be able to accomplish in 5 million years with the Colorado River.
It also gives you a pretty strong hint. There was probably another incredible canyon that was there a long time ago that's gone now, and we're seeing...
Right, that's completely not even there anymore. Right.
We're just seeing the bottom part of that canyon.
Yes. Jerry.
From what you're saying, there's a lot of stuff, but up north, the flood started digging away the basalt rock. So the covering over that wasn't quite as thick. How come there's such a major difference for the thickness down by the Grand Canyon and up in Washington?
Well, there's sedimentary rock under the basalt.
I was thinking that might be the case, but is it the same kind as?
No, because the whole western United States is what they call exotic terrains. In other words, you have, again, this is basic geological stuff, but with the westward movement of the North American plate over the last roughly 70 million years, as the Atlantic is opening up and spreading, you have Africa and Europe moving to the east, and you have North America and South America moving to the west. We've all seen, right, the images showing if you welded the continents back together and how they fit. Okay, well, that's because they were once part of a single landmass that fractured and then has split apart. Well, as what we see now as the North American continent was not originally the North American continent. It's like as it's moving to the west, it's piling all of this stuff up in front of it. Island arcs particularly. And many different types of crust. You know, there are, on one end of the crustal spectrum, there is continental crust, which is mainly granitic. And then on the other end of the spectrum is basaltic crust, which is mainly, or oceanic crust, which is mainly basalt. And in between those two, you've got a whole mix, but those are the two ends of the continuum. And they're basalt and granite, of course, are igneous rocks. But then mixed in there, you've got all kinds of sedimentary rocks. Now, in order to have a sedimentary rock, you have to be able to have an erosion cycle and an accumulation cycle. Because sedimentary rocks are not original rocks. You know that, right? If you're seeing a sandstone or a limestone, you're looking at secondary rocks or tertiary rocks that were created from earlier rocks that were, dissolved or shredded, taken apart, and then reaccumulated as new rocks. Now, what you're asking, Jerry, is up in the Columbia Basalt Plateau, you have anywhere from 1,000 to about 3,000 or 4,000 feet of black lava rock, basalt, that flowed out of great fissures in the ground, but buried ancient sedimentary terrain that's probably 200 to 300 million years old. So when you go, like up around Hudson Bay is what they call the North American craton. Once you got up there, it's the nucleus of the North American continent. It's this big granitic mass. Imagine Stone Mountain, but millions of times bigger. And you've got this big knob, and that's the North American craton. And it's that thing that's been moving, and as it's been moving, it's been piling up all of this other kind of crust in front of it. So when you go out west and you see those mountains, you're looking at the stuff that's been scrunched up as the North American craton has been shifting through the crust. Stuff is piling up in front of it, almost like a bulldozer, just moving along, pushing this stuff up so it's mounding up in front. And it's a lot of different stuff. It's a lot of stuff whose origin is very diverse. So when you're traveling out west, if you're looking at the geology, it's a lot more complicated, than other parts of the country because of that. There's so many different types of rocks that it's taken geologists 150 years to sort it all out.
How did Hudson Bay get in that?
Hudson Bay, that's an interesting one. I think that Hudson Bay is probably the core of an ancient giant impact structure. And as a result of that, you've got deeply fractured rock. And then when the glaciers come along, they want to tend, because they go to where the fractures are, they tend to excavate. Glaciers, when they form, they like to excavate rock. And so they can zoom in kind of and start excavating where the rock is the most susceptible. And I think that's what it is. And then even deepen that basin. And it turns out that over Hudson Bay was where the ice was the thickest. It was perhaps over 2 miles thick at Hudson Bay. That's a lot of ice. Dorita, you got something you want to throw in?
It is about this part of the country, but why is it like Stone Mountain and all up there, because you've got granite predominantly and everything. You can't even hardly dig to make a garden unless you run into granite rocks and everything. And in North Georgia, you've got all the red clay.
Well, the red clay is a residuum. The red clay has been eroded. I mean, what happens when granitic rock decays, it's really old, it decomposes into its constituent elements. The red clay comes from the granitic rocks. Lots of iron oxides in it, that's why it's red. And it's a testimony to the fact that there has been lots of erosion over the southeastern United States.
North Georgia
Well, I've
River
heard that
takes
the
you
dirt
to
on
Marble.
the Piedmont Plateau is the youngest dirt in the world.
Oldest floor in here.
Yeah, that could be. I mean, that could be.
How much does the continent move? What's the rate of movement?
The rate of movement is probably a couple of centimeters. Yeah, I would say, it varies from place to place, but you could figure a couple of inches per century.
3 inch, and also the east coast of the United States is coming up, and the west coast is going down too. The east coast is about 3.5 inches higher now than it was in 1900. That's the reason the Okefenokee is going dry. You go out on the west coast, the San Andreas is doing two things. The Pacific plate is turning to the northwest and pushing down on the North American continent.
Okay, well, not to get too far into the geology. I love talking about geology, but my whole point was the Holocene is the last 10,000 years. And with the advent of catastrophism, which began with the advent of radiocarbon dating, unintentionally it led to the emergence of a new catastrophic model of Earth change. So what happened with radiocarbon dating is by the 1970s, everything was now known to be happening much faster than it could have been with the Milankovich timing. So slowly the Milankovich models have lost their hold on climate change thinking and environmental change and so forth, and essentially have been replaced by nothing. So you had 40 years ago, most environmental people, geological people, people who looked at ancient climate, were pretty well satisfied that they had it figured out. What caused ice ages, what caused interglacial ages, and so on. And it was this vast rhythm that unfolded slowly through time. And of course, in that context, you've got to understand that on that level of temporal unfoldment, it doesn't bear much relation to us here and now. That was the main thing. If we're looking at a cycle that takes 100,000 or more years to transpire, and within that 100,000 years, it's a gradual, uniform process, that doesn't really relate too much to our present situation, only in the long term. You know, if we're thinking in terms of human societies 10 or 20 or 30,000 years from now, something like that would then become a factor. But it has no relevance to thinking about, you know, the status of human society on Earth in the next year or 10 years or even 100 years. However, the Milankovich models, like I said, are no longer they no longer do the job of explaining the rapidity with which environmental and climate change has taken place. What have they been replaced by? Like I said, nothing. There's nothing out there that essentially now the scientists are in agreement on. This is the major driving force behind climate change, behind Earth change, and so on. What I've been saying in here for the last 2.5 or 3 years, or whatever it's been, is that in order to come up with a new model, we have to expand our thinking to the cosmic domain. If that's one insight you take out of this, that would be one of the most important, is that we have to start thinking of Earth change in terms of cosmic phenomena. Because when we see that glacial, interglacial cycle, what we're seeing is the response here within I call it the terrasphere. The terrasphere being the combined atmosphere, hydrosphere, biosphere, lithosphere, etc. All of those combined we'll call the terrasphere. When we see these abrupt changes on the terrasphere, what we're seeing is the response, Earth's response to changes in the cosmic environment. And those changes in the cosmic environment can take a variety of different forms. And they can happen slowly, but they can also happen extremely fast within the human time scale. And that's what we've seen with the transition into the Younger Dryas. We've seen a 10-degree freezing. Can you imagine Georgia going from the... Try to do this. Imagine, and this will give you... This is a very realistic analogy for the onset of the Younger Dryas. Imagine if the climate of Georgia, as it was now, went into the climate of, say, Labrador. And now imagine that change happens in perhaps 2 to 3 years. Where would that leave us?
They said it happened last time in 10 years.
What? You said
That's
what?
what I've read.
Well, that would be 10 years is actually the maximum.
Yeah.
The maximum. Even if it happened in 10 years, what would that imply? I mean, it's not like within that 10 years, you can't even assume there's going to be a smooth transition. And what else would be going on if the climate is changing that severely, that quickly?
Crops, trees. For one thing, the trees would die.
Certainly. We could say this with confidence. Even if it took 10 years, if it started tomorrow, we'd be gone long before the 10-year transition period was over. We would be gone in 2 to 3 years maximum. Because the changes within 2 years would be enough to essentially destroy agriculture across the entire continent. So where would that leave us? Now, the thing is when we look at the Younger Dryas, it's not an anomaly. We now know that the Younger Dryas has happened dozens of times, and we don't know what caused the Younger Dryas. That's the problem. We're sitting here realizing that all of these old models that we were, raised up with, these models of Earth change, are completely obsolete. The public at large, that is not even on the radar screen. You don't turn the TV on. If you hear anything about climate change on television or in mainstream media, it focuses almost exclusively on what we humans are doing to the climate. But can you blame the Younger Dryas on humans? Can you blame the transition, the instantaneous glaciarization, they call it, that happened 26,000 years ago? When the climate shifted, 26,000 years ago, the climate shifted from a climate similar to the present into full glacial cold. Now, it took 5,000 years, 6,000 years for the huge ice masses to form over the continent. But the climate change that caused the beginning to accumulate, that happened almost instantaneously in the geological sense. It happened so quick that they can't discern. Whether it happened in 100 years or 10 years or 1 year, it happened so quickly that they can't discern a span of time during which a transition took place. It was as if, it was like this. The switch, somebody flipped the switch, and then all of a sudden, here we are, we're in glacial cold, boom, it switches. Now, if I come in and the furnace is not on, I flip the switch, the furnace comes on, right? Now, immediately the furnace is on and starts heating up. Of course, there's going to be a lag period, right? So it's just like that. There's a lag period. The temperature dropped. The snow began to accumulate. But, here's the mystery. And this is what's befuddled glaciologists and climatologists and so forth. And they still don't have an answer for it. And it's simply this. If you drop the temperature, if suddenly the temperature drops 10 degrees on average, now that could translate into a regional temperature drop of 40 or 50 degrees. I mean, it might mean that the difference between the average temperature in Georgia in the winter, which is probably, 40 degrees? Something like that?
More than that now.
More than that.
36, 38 degrees.
Somewhere like that? Well, it means that the average temperature in Georgia might be zero. Might be zero.
See, there hasn't been any snow, very little snow or anything like that for the last 10, 15 years. When I come to Georgia in 1961, we had snow.
Well, remember now.
I remember down to get 8 and 10 below zero here.
Remember, in the year 1400, the global climate went through a cooling phase. And all of the glaciers worldwide began to expand. And in fact, the Little Ice Age, it's surmised by most glaciologists that have looked at the Little Ice Age, that the amount of ice that grew during that 300 roughly year period was the greatest amount of ice throughout the entire Holocene. In other words, to exceed the amount of ice that accumulated during the Little Ice Age, you've got to go back 12, 13, 14,000 years ago. Well, the interesting thing is that when you look at the timing of the smaller cycles within the larger cycles, you see that there has been a 300 to 400 year cycle. The Little Ice Age was preceded by the medieval warm period. The medieval warm period was preceded by the period doesn't have a name, but it's exactly the period, a cooling period that coincides with the Dark Ages. And we've talked about that. From roughly 540 AD up to about 1000 AD, there was a period of global cooling that essentially culturally we refer to as the Dark Ages. And as it turns out, it's interestingly enough, it appears that there really were literally dark ages in which months would go by without the sun showing itself. And those are in the annals, in the records. I've read some of them to you. And this we're talking about, the mid-500s, and that was followed by this period of global cooling. Then along came the medieval warm period, and with the medieval warm period, suddenly you had the agricultural belt shifted hundreds of miles farther north from what it had been. The altitude at which you could grow crops shifted hundreds of feet higher above sea level. The growing season increased by a month or more. Well, those changes were enough to create food surpluses all over Europe. And what you see is the most rapid expansion of the human population and human lifespan in the last several thousand years occurring during the medieval warm period. As it turned out, the medieval warm period was a very beneficial time for human beings and human societies. It was during this time, of course, that Greenland was occupied, that Iceland was occupied, and so forth. That came to an end between 13 and 1400 roughly, and we went into the Little Ice Age. And that caused major disruptions. It caused collapse of agriculture. It caused famine, the famine and the malnourishment that was a consequence of the contracted growing seasons led to people's immune systems getting weak. Opportunistic diseases like the bubonic and the black plagues then came along and exploited those weakened immune systems. And so you had, now during the onset of the Little Ice Age, you had a crash in human population. Whereas during the interestingly and ironic, if we look back through history, it appears that the periods of global warming were a lot more benign for human society than the periods of global cooling. Around 1850, the glaciers worldwide reached their maximum. And you can still see the moraines created by those glaciers. And they begin to recede. And as they begin to recede, they left behind lakes and all kinds of interesting things that helped geologists figure out. See, this was a good example of scale and variance. It was the geologists looking at the effects of the Little Ice Age that gave them the eyes to see the Big Ice Age, because they mirrored each other just on a smaller scale. Well, Sam, the warming you're talking about has been going on for a century and a half. I've shown you pictures in here. Maybe you've forgotten. I've shown you pictures in here of glaciers photographs taken in the 1860s and 1870s. You can see they have been contracting since the mid-19th century, with some exceptions. Hubbard Glacier in Alaska has been growing enormously. That's why the biggest flood, interesting, check this out, the biggest flood, suspected the largest flood in the Holocene from a glacier outburst flood, was the failure of the moraine dam caused by the Hubbard Glacier in 1986. It was 3 million cubic feet per second. I don't know if you remember when we've been talking about these great magnitude floods. How much was the Missoula Flood?
400 feet deep and 65 miles an hour.
You can figure 700 to 800 million cubic feet per second. The average flood stage of the Mississippi River, flood stage about 1 million cubic feet per second. The Amazon River, where it discharges into the Atlantic Ocean, is close to 3 million. That's the largest discharge of any river on Earth to the ocean. Now, the Hubbard Glacier was roughly the same discharge as the Amazon, except that it was it happened over a period of about a day and a half, and it was through a channel 1,000 feet wide between a rock face and a glacier. So that was the Hubbard Glacier, 3 million cubic feet per second, an order of magnitude bigger than any other documented modern ice-dammed flood. It happened, interestingly, I thought rather coincidentally, on October 8th. So the greatest documented natural flood happened on the same day as the greatest documented natural fires that we were talking about last week. Connection? I don't know.
you know,
but I wouldn't rule it out.
in 1987, I was in Anchorage, Alaska. Went over to the glacier, and you could take a rowboat and row out to the glacier there, right on the outskirts of Anchorage. I saw some pictures the other day, and it was 7 miles to the glacier now. It is that much. It's warmed up since the early 70, 80, somewhere along in there, to right now. It has backed up 7 miles, that glacier.
So an extraterrestrial impact could create.
No, those aren't the same thing, Elizabeth. That's different.
But it could create global warming and global cooling, depending on how it would affect.
Okay, well, let me get back. Inadvertently, you put me back on my train of thought that I was on, that I deviated.
Do I get a bonus?
We'll talk about that after class. See, here's the problem with an ice age. What I was saying was, you cool the climate down. You have the thing, what's the hydrological cycle? What's the hydrological cycle?
That's where you get evaporation, makes a cloud.
Water is evaporated up out of the oceans. Just like Jerry said, it forms clouds. The clouds go over the land. It precipitates out, usually as rainfall or snowfall, sometimes as sleet and other things, but mainly rainfall and snowfall. If it falls in a northern climate during the winter as snowfall, it accumulates and there's a temporary interruption of the cycle until spring comes, and then it thaws, and then the cycle continues. With the onset of a glacial age, it's sort of like, imagine how the cycle is interrupted for 6 months. If you live in the northern United States, you know that once you get to about late November, early December, precipitation falls as snow, and it doesn't rain again until probably April or early May. So you've got this interruption of the hydrological cycle, right? But you know spring is going to come along, and then the snow is going to melt away, and then you're going to have warmth, right? If an ice age comes on, imagine it's the same thing, except that spring just never shows up. In fact, well, it eventually does 10,000 or 15,000 years later. But that'd be a very accurate way to think of it. Oh, so now that the snow does not melt in the spring, it just rolls right over, and the next year's accumulation of snow falls on top, and then the next year, and then the next year. And after about 3 or 4 or 5,000 years, you've got thousands of feet of glacial ice formed. But the problem with that is simply this. When you lower the temperature, you basically slow down the hydrological cycle. When you look at the onset of a glacial age, what you see is the very rapid accumulation of huge glaciers over literally millions of square miles of landmass, up to thousands of feet thick, which requires essentially it requires a hydrological cycle on steroids. But the problem is the climate's obviously cooler, or you're not going to accumulate the ice. So there's a major contradiction right there that has not been resolved. But again, the attempts to resolve that paradox have all been based upon models that are exclusively Earth-based. As soon as we began to allow our thinking to expand to the cosmic domain, we discovered that there are forces and phenomena that could achieve such an interruption of the hydrological cycle. At the same time, here's the problem. How do you simultaneously shut down, put the Earth into deep freeze, but then you accelerate the evaporation and precipitation cycle? How do you do it? Well, it's what you were suggesting, Elizabeth. You can do it by an accretionary process. You can do it by introducing materials and energy from outside the terrasphere. Now, in order to precipitation, you have to have, every raindrop has a nucleus. So in the aftermath of Tunguska, remember what happened in the aftermath of Tunguska? There were these strange rainfalls that lasted for several days. A lot of other of those type of cosmic events have been associated with rainfalls. it created this fine dust in the atmosphere, and those little particles of this cosmic dust formed nuclei around which raindrops accumulated and fell to Earth. Now, what would happen? We have to begin thinking now about the kinds of consequences of things like comets exploding in the atmosphere, comets and asteroids landing into the ocean, comets and asteroids landing onto ice sheets, comets and asteroids hitting the ground, causing fires, but maybe in some scenarios simultaneously hitting the ground and hitting a water source. If you could simultaneously hit the ground and create fires and inject lots of dust into the atmosphere, at the same time you land one in the ocean, I think you've got all the ingredients you need. You've got an enormous amount of particulate matter injected into the atmosphere, as well as huge amounts of water vapor. And if the water vapor precipitated out, the particulate matter did not precipitate out, what you would end up with is a canopy, a veiled canopy over the atmosphere that would reduce the amount of heat getting to the surface. So I think, again, that's a very rough estimate of the model, but I think that's one way you could explain it.